Hello to everyone. This work is dedicated to studying of magnetic properties of molybdenum disulfide and tungsten disulfide powders. The main idea is to obtain materials with a semiconductive and magnetic properties, achieving it by the doping magnetic and antiferromagnetic elements. Theoretical and experimental studies has shown that two-dimensional transition methods halcoinides such as molybdenum disulfide and tungsten disulfide doping by magnetic elements, structural defects or manipulation of edge effects can include ferromagnetism. It is possible to induce ferromagnetism in molybdenum disulfide not only by doping, but also by proton irradiation on annealing. Molybdenum disulfide consists of many particles deposited on a special electrically conductive substrate placed to the microscope stage. The molybdenum disulfide nanoparticles are annealing on the quartz tube furnace purge and fill it with argon gas at the temperature of 700 Celsius for 1 hour. Images of the same sample but different places are presented before and after annealing. Analysis of data shows that there was no visible change in the particle morphology. The image shows that the particle size ranges from tens microns, maybe more, to tens of nanometers. Large particles of the order of units of microns and more have a predominantly flat surface on which smaller particles are located. Particles are characterized by an arbitrary arrangement relative to flat surfaces. The presence of large flat particles indicates the existence of easy cleavage planes in the crystal lattice of the substance. Medium and fine particles have different shapes up to curved. Elemental analysis of the pristine molybdenum disulfide sample revealed the presence of the sulfur vacancies, oxygen and copper. After annealing, the amount of oxygen, copper, and molybdenum remains the same. Only the amount of sulfurs increases and non-stoichiometry increase also. A possible reason the change of the heterogeneity of the elements distribution in the probe. We assume that due to non-stoichiometry, there is a presence of oxygen vacancies and changes in the molybdenum valence, or the appearance of uncoordinated molybdenum atoms. And for non-annealed, it's 0.0036. With maybe is per magnetron, and if U is formula unit, and chemistry is empirical formula for an ionic or covalent solid compound used as independent entity for the stoichiometric calculation. Thus, we assume that indeed defects or edge effects are a consequence of the ferromagnetism which we observed in molybdenum disulfide powders. Tungsten disulfide powders are diamagnetic. The inside shows that paramagnetic contribution obtained as a difference between the curves for low and room temperature from 100 Kelvin and 293 Kelvin respectively. Thus, in the low temperature region, there is a paramagnetic signal, probably from tungsten, and with a predominant diamagnetic phase. To determine a critical concentration of total defects, which can lead to the formation of magnetic response, we use a percolation approach. Using the criteria percolation theory, earlier it was shown how to percolation threshold of the long-range magnetic order is established mathematically. According to the theory, long-range magnetic order in the system occurs as soon as the infinite cluster forms. The distance between the defects which form the infinite cluster and therefore fulfill the percolation condition or threshold is defined as percolation radius. To determine percolation radius, the calculation was performed for the nanoparticles of different sizes to ensure that the percolation condition is actually fulfilled. In this case, the ratio between the number of magnetic defects in the infinite cluster and total number of magnetic defects in the system remains unchanged in particles of different sizes. Below we assume the following dependence of magnetization on applied quasi-static magnetic field. Where the first term is purely paramagnetic PM contribution and second can be superparamagnetic contribution of nanoparticles. The values delta M can be non-zero, reflecting a very small device-related systematic error shift. At room temperature, the fields should be much smaller than 800 keV. The number of magnetic ions in the paramagnetic part of the sample can be obtained from the Curie constant, valued in the Curie-Weiss law for the Hem equal to Cv over T minus theta. In case of interaction between ion spins, the temperature theta is negative. So here we have our theoretical modeling. A lot of following Binder and Young work, which is listed as a reference as integration in last equation reflects the number of elementary spins which contribute to the magnetic momentum. Mu is given as PM nano-inclusions, thus to its superspin should be different from different inclusions. The moment can fluctuate slightly or strongly around average value mu s over temperature independence on the sharpness of its distribution function. The function is defined as mu s over t as integral of mu s depending on mu s minus t over delta mu. The magnetization amplitude of SPM contribution is equal to MP equal S mu, where NS is the average number of superspins in 1 gram of the material, having the average magnetic momentum mu s. Depending on the spin value, one can use Langevin LF or Brillouin function for the function describing SPM contribution. Conclusion. In our work, the magnetic properties was studied, comparing experimental results with the models and theoretical calculations. The manifestation of the ferromagnetic properties of molybdenum disulfide could be explained due to local structural organization of a few layers molybdenum disulfide on the edges of the particles, not stoichiometry of the samples. vacancies and negligible admixtures. Annealing of the molybdenum disulfide leads to an increase of magnetization and decrease of coercive force. Tungsten disulfide is diamagnetic from a low paramagnetic contribution at low temperature. Obtained results are useful for application of the low-dimensional transition metal dichalcogenides in the spintronics, magnetronics, and strain engineering. Thank you very much for your attention.